Morning. This is Patrick McDaniel. I'm a professor at Penn State University working with my student Nicolas Papernot on adversarial machine learning. We're going to start today by describing a little bit about adversarial machining, what it is, why we should care, and then talk a little bit about some of the attacks. So let me cut over to the slides here. As I mentioned, we've been working on adversarial machine learning for the last couple of years. But it's important to take a step back and ask ourselves some questions about, well, generally, is security relevant to machine learning, and what should we worry about? So if we think about, as somebody who works traditionally in system security, it's important to think about, well, what are the application domains that machine learning have become important to? And there's sort of some canonical examples of autonomous vehicles and things like that. But certainly things like data analytics has revolutionized the healthcare and financial systems, as well as many other different fields. And so when you're considering security and the use of machine learning, it's important to ask yourself, well, who would anybody actually want to manipulate these systems? And for all of the examples I just gave, the answer is, of course, yes. I'm sure most of our audience could identify many examples of machine learning systems that whose either results or data is extremely sensitive, and therefore we need to think deeply about security in these systems. So what do I really mean by attacking a machine learning system? So let's take a look at this example here where we have an autonomous vehicle. And in this autonomous vehicle, it's driving around the streets of, I'm here out on the West Coast this morning. It's out here on a sunny day, and it's recognizing objects as it's moving through the domain. And when I say recognizing, what it's really doing is it's using its image processing. For example, if we see here on the chart, we see something like a stop sign. It recognizes stop sign by looking at samples, images, and trying to infer what the image is. So in this case, we recognize something as a stop sign, and then we use the features of that stop sign, the individual pixels and the secondary elements, things like the shapes of the sign, to tell us something about what that sign is. And that's where machine learning comes in. The machine learning system will then take all of those inputs and use them using some system. In this case, we actually have a deep learning system to identify what particular object it is. In this case, the autonomous vehicle recognizes that it is a stop sign with high probability and functions correctly in this case. But now let's think about an adversary who might actually want to manipulate this system. So now you have an autonomous vehicle, and say I have some way of manipulating that image, either by manipulating the sign, by painting the sign, or actually getting into the data pipeline inside the car, modifying the images. But in this case, as an adversary, I want to control what the car does, and I want it to misunderstand what it's seeing. And in this case, we want it to not understand that it's a stop sign. We want it to infer that that particular image is something like a turn right sign, as illustrated here. And that is an example of a attack. In this case, we're trying to induce the machine learning system to make the wrong decision. And what's important is that wrong decision is controllable on some level by the adversary. And therein is the vector by which the adversary can manipulate or harm these machine learning systems. So let's talk a little bit about this notion of a threat. So there are really, we've been looking at what we call threat modeling machine learning systems for a couple of years, and there's a number of different classes of attacks. And they really represent different strength of an adversary. As an adversary gets stronger, they have more ability to control the system. The easiest or simplest or weakest attack is something we just simply call a confidence reduction. So if we have something like, and we'll talk almost entirely through the next few minutes about a classification, where we have some sort of input domain, and we're given a sample, and we're trying to decide what category it falls into. So in that categorization, confidence reduction is the simplest attack, and basically all we're trying to do is reduce the confidence of the machine learning system in its decision. So we'll manipulate, for example, in this case, an image to get it to think, well, I'm not 100% sure. And this is important where the information is fuzzy, where the information is not entirely known. And by manipulating the system and reducing the confidence, then we reduce the strength of the decision that's made by that machine learning system. And where we're making sensitive decisions based on the output of that machine learning system, then that becomes, that reduction of confidence can corrupt that entire decision-making process. The second attack is really simply misclassification. And in misclassification says, okay, I don't really care. And as an adversary, all I want you to do is get it wrong. I don't care how you get it wrong, just get it wrong. And in this case, what we're really talking about is taking an input, modifying it in some way that falls outside of the actual output class of the sample. In the case of our stop signs or our signs on roadways, as long as it's not a stop sign as an adversary under this attack, then we have been successful. Targeted misclassification is where we are trying to generate a sample which is not in the input class but gets classified as a particular input class. In this example, you can see this class has been identified as a cheetah. You can tell it's a noise sample, but in this case, we knew something about the adversarial, about the machine learning system to generate this white noise, which is not random, which is exploiting something within the model. But the important thing is, an adversary, I can give you a sample which is not a legitimate sample, but which you classify as a legitimate class. Now, the most powerful one, and the one that perhaps has gotten the most publicity, are the source target misclassification attacks. And that's where you take an input class of a particular type and, as an adversary, modify it into a particular target classification. That is, you modify the input sample so it is targeted to a specific output class controlled by an adversary. So let's think about a good example of this. So say you have a machine learning system which is recognizing handwritten digits on checks. So you were working for a bank. So one of those digits is a legitimate one. As you can see here on the chart here, the top is a legitimate one that was handwritten. That's actually from the MNIST data set, which is actually handwritten digits. But we want to modify it in such a way that we want to turn it into some other number. In particular, we want to manipulate the check in such a way that, as humans, we could look at the check and it looks like just a handwritten digit, but it might have a little noise. But the machine learning system actually misclassifies it. And so we give it a source, we have a source, and we want to turn it into a specific misclassification. So what you see here in the bottom is a good example of this. One, by just adding a little bit of noise on a particular machine learning system, we can turn it into something, I believe that is an 8. The important thing is that's the strongest adversary, and basically the adversary in that model can control the output of the machine learning system in any way that they want. And that is a quite powerful adversary indeed, because they can subvert the entire logic of the system, which depends on the decisions that are being made by the machine learning system. On the other domain, and another axis of considering adversaries, you want to think about adversarial capabilities. As you do threat modeling and security, you want to think, well, what are their assets and capabilities? So we're going to sort of flip the strength axes that we just discussed, and we'll start talking about the hardest being having the least amount of information, and we'll work our way up to the strongest adversary, which has a lot of information. So at the very bottom, we're going to work our way up. The simplest adversary, all they have are individual samples. Basically what you can think of that is that the simplest attack simply just assumes that you have some collection of sample data, the input training data, for example. It turns out that this is a very, very weak model, and it's difficult to know, unless you have a lot of additional information, how to attack a system with just a subset of the input to use. Now, a little bit of stronger model, and this actually falls out of the cryptography literature, is something called an oracle. And an oracle in a machine learning system is just a system in which you have a machine learning system that you want to attack, and that machine learning system acts as an oracle. You can give it a sample and it will give you an answer, an output classification and a confidence interval, for example. And you can use that information to attack the system. So what's important here is that you can have an interactive session where you can extract information about the machine learning system's internal model. Now, both that first sample-based attack and the oracle model attack are referred to as black box attacks. And in black box attacks, you have no information about the input system itself, about the machine learning, the internals of the machine learning system. A stronger attack actually looks at, moves into what we call the white box domain, which gives us increasing information about the internals of the machine learning system. The first one is actually training data, where you have a significant chunk of the training data that's used to model to attack the system. I'm sorry, the training data that's used to train the machine learning system, and therefore you have something that's representative of the input distribution for which the machine learning system is built. A stronger model, again, would be architecture. That actually tells you what are the internals of your system, but potentially things like the weights in a deep learning system. And then finally, the strongest adversary has the architecture and the training data, and has essentially a complete duplication, has all the information you need to know, essentially the entirety of the model. Now, those last three attacks fall into a category called white box attacks. And white box attacks, why they're called white box, is it's a white box. You understand what the internals of the machine learning system is. And what's interesting is that it turns out that, not surprisingly, that the more information you have about the machine learning system, the easier it is to actually attack those systems. So let me just kind of wrap up before I hand off to Nicolas here and talk about the first, a first white box attack. So this is called the Jacobian-Based Saliency map approach, or JSMA. But basically, this is just an algorithm for generating adversarial samples. So the conceptual core of the JSMA is something called a saliency map. And to think, the way to think about a saliency map is it just tells you what's important, which attributes are important for each output classification. So let me just kind of walk you through these algorithms. So we begin with a legitimate input that we are going to send to our system. Okay, this is an example of a white box attack. So we've got a legitimate input sample. We're going to take a look at that sample, and we're going to compare it to the saliency map. And that saliency map tells us what are things that are important to a particular output class, such as 1. We're actually going to turn this 1 into a 4. And that saliency map tells you which features are most important for things being 1. Now, if you think about that conceptually, you can think about, if you're looking at handwritten digits, pixels that are on the vertical, that have a vertical line in the middle, those pixels, those features are most important to oneness. And you can think conceptually what kinds of pixels are more important for 4s. But essentially what you take is you have your saliency map, you take the inputs, the attributes that are most important to 1, and use the saliency map to say, okay, these are the most important, and I will perhaps reduce those. I might, in this case, this is just sort of black and white images. I might eliminate one of these, or reduce the intensity of the most important attributes, and then I will bring up the attributes which are most important for the digit 4. And what you'll see is something on the right. Now, what you're going to do is you're going to do this one feature, or maybe a couple features at a time, but you can go through this loop. And what you're essentially doing is you're pushing, as you modify these attributes, you're pushing it away from the 1 and closer to the 4. So you're pushing it from the 1 to a 4 class, and essentially what you're doing is you're pushing it across the decision boundary of the model. So what is the saliency map? Well, basically the saliency map is just as I described. So it's a map that says, okay, here are all of my input features that I'm going to be making decisions in this machine learning system. And I'm going to look at those things which are most highly correlated with my source, and most highly correlated or negatively correlated, depending on how I want to approach the system, with a particular target. And so you use that map to select which features are to modify. And it turns out for many of the systems we have tested, you don't really need to change that many features, actually a couple of percent. And it's fairly easy to move it across that decision boundary. So let me conclude. This feature, the image last here is really shows you how effective we can be. This is actually our handwritten digits. And on the y-axis here, you have all of the input classes, and the x-axis you have the target classes. And you can see how we've modified all of the images from a source input class to an output class. Now, what you'll note here is that some of these are noisier than others. And it turns out that some things are just harder to transfer. It's harder to move, say, a 5 to a 1. And conceptually, that's not particularly difficult to understand. So with that, I will turn it over to Nicolas to talk about black box attacks.
Thank you, Patrick. So in the few slides that we just saw, the adversary always had access to the model parameters and was using these parameters in order to compute the perturbation needed to find adversarial examples. Instead, in the upcoming slides, I'm going to show another class of attacks which are called black box attacks, and where the adversary has much less information about the machine learning model it is targeting. So basically, Patrick discussed a scenario where the adversary had access to the model parameters and other things like the training data, and was able to find perturbations that mislead that model using that information. Here I'm going to consider another scenario, which is a black box attack. And the adversary in this case has no access to training data, the model architecture or parameters, and not access to the model scores as well. And instead, the adversary is only able to interact with the model as an oracle, so it can submit any input of its choice and observe what the label predicted by the machine learning model is. So this corresponds to platforms such as the ones hosted by Amazon and Google, where the model is trained on the platform and you can access using an API. It also corresponds to the example of an email service provider where the adversary can try to evade the spam filter, which is detecting malicious attachments, by first interacting with it by submitting examples of malicious files and observing whether they were blocked or not, but it cannot know how the spam filter made that prediction. So in these types of attacks, the black box attacks, we have two main challenges. Is first, we don't have knowledge about the machine learning model, and second, we don't have any knowledge about the training data. So I'm going to first explain how we alleviate the lack of knowledge about the model that is being used by the defender. So we're using something called adversarial example transferability, and it states simply that an adversarial example crafted to mislead a first model A is also very likely to mislead a different model B. So in this case, it allows the adversary to first interact with model A to find an adversarial example, and then submit directly to a second model B, which is the victim, without needing any information about model B. So depending on the pairs of models that you're considering to perform the black box attack, we have different variants of transferability. Here we have two neural networks trained on different data sets. So we have cross-training transferability. The adversary would interact with the first neural network to find an adversarial example and then submit that same input to the second neural network. What's more surprising is the scenario where the two machine learning models are trained using different techniques. So here in this case, the adversary would first interact with the neural network to find the adversarial example, and then submit that input to the decision tree, which is also likely to misclassify it. And now I'm going to present some experimental results to give you an idea of how likely transferability is to hold in practice. So here we first have results about cross-training data transferability. So we're taking a data set and splitting it in 5 partitions, A, B, C, D, and E. And on each of these partitions, we're training a machine learning model using the same technique. And we're evaluating how likely adversarial examples transfer between these 5 models. So on the left, the first matrix, you have on the y-axis the model that was used to craft adversarial examples. And on the x-axis, you have the model that was used to test the adversarial example. And you can see in the matrix the transferability rates, which means the error rate of the target model on adversarial examples computed by the source model. And so you can see when the models are trained using logistic regression, we have very strong transferability across all pairs. In the matrix in the middle, instead, we have support vector machines. So we're repeating the same experiment, but replacing logistic regression by support vector machines. And what you can see is that the diagonal stands out much more, which means that an adversarial example is much more likely to be misclassified by the same support vector machine it was crafted on than a different one. And when we repeat the same experiment with deep neural networks, we have sort of an hybrid property where, depending on the pairs of models, we have between 50 and above 80% transferability. What's more interesting for black box adversary is to be able to transfer adversarial examples across models that were trained using different techniques. So here we're repeating the experiment, but this time training a different machine learning technique for each model. So we have a deep neural network, a logistic regression, a support vector machine, a decision tree, and a nearest neighbor. So on the y-axis, we have again the model on which we crafted adversarial examples, and on the x-axis, we have the model on which we tested the adversarial example. So you can see here the transferability rates are high for many pairs of models, which allows the adversary to attack a model regardless of the technique used by the defender. Second, you can also observe that transferability is not invertible. So it is easy to use here a neural network to target a decision tree. You have a high success rate. However, using a decision tree to target a neural network is not as successful. So you may wonder, what if the defender were to use an ensemble of models trained each with a different technique? And that is what we evaluated next, where we took the 5 models that we considered previously and took a majority vote among their predictions. And you can see that the transferability rates are still relatively high and at an acceptable success rate for the adversary. So using transferability, we can alleviate the first challenge, which is the lack of knowledge about the model. We can simply, as the adversary, train our local substitute model to target a different model. However, we have an additional challenge is we don't have any training data to train the substitute model. So we're going to use instead synthetic data, and I'm going to show you how we do so. So the process involves querying the remote machine learning system, because if you remember, we assume in our threat model that we're able to select any input and observe the machine learning model's label prediction. So here the adversary begins by selecting a few representative inputs of the machine learning task, so maybe 10 per class. And it sends these inputs to the remote system in order to observe what label is predicted. I'd like to stress that the machine learning model only returns the label and not the model score. So using these labeled data points, the adversary can train the local substitute, which is a machine learning model, on its machine. Initially, this model is not going to perform very well on the task that the remote system is solving. So the adversary is now going to generate synthetic inputs using the Jacobian matrix of the local substitute, which allows the adversary to identify input regions where the local substitute has a lot of variation, So where more queries are required to get a better estimate of how the remote system makes predictions. So if the adversary successively generates synthetic data using the local substitute and then use the labels returned by the remote system in order to improve the training of its local substitute, it eventually basically extracts a copy of the remote model into the local substitute, and the two models solve the task in a similar manner, which allows the adversary to use the local substitute to generate adversarial examples that transfer back to the remote system. So now I'd like to show you how combining these two points, we performed black box attacks against real systems. So we considered 3 remote platforms, MetaMind, Amazon, and Google, and we all asked them to train one machine learning model. So we had 3 remote machine learning models that we were able to access through an API, which returns the label for any input that we send the API. So we conducted the extraction attack that I just described in the previous slides, and we evaluated what is the error rate of the adversarial examples that we craft using our local substitute when we submit them to the remote system. And this is what you see on the last column. So for MetaMind, 84% of the inputs that we crafted after extracting our local substitute were misclassified by MetaMind. For Amazon, it was 96%, and for Google, 97%. So what's interesting is that the number of queries that we have to make before being capable of crafting misclassified inputs at such high rates is an order of magnitude smaller than the number of training points that the Oracle used, so the remote system used to train the model. And what's also interesting to note is that as the defender, so the remote system, is using a more complex machine learning technique like deep learning, this increases the number of queries that the adversary has to make in order to extract an accurate approximation of this model. So here you can, for instance, compare the number of queries made for Amazon compared to MetaMind, which is much higher. So now we saw in the previous parts of this talk how we can attack machine learning using white and black box attacks. And before we conclude, I'd like to give a few highlights of how difficult it is to defend against these attacks, and as well as give you an idea of the benchmarking efforts that we've been contributing to. So first, there have been a few defenses that were proposed in the literature, and unfortunately they almost all fail to defend against adaptive adversaries. So 2 examples of such defenses are adversarial training and defensive distillation. So adversarial training is very intuitive. It consists in injecting adversarial examples during training in order to help the model better generalize to these perturbations. Defensive distillation is another defense where the defender is training on model scores instead of hard class labels, which allows the decision surface to be smoother and have smaller gradients, which means it is harder for the adversary to find inputs that are misclassified, such as adversarial examples. However, we found later that these defenses are vulnerable to black box attacks because of something we called gradient masking. And you can get an intuition of what gradient masking is by looking at the figure. So if the defended model is using a defense like adversarial training and defensive distillation, what happens, as we observed empirically, is that instead of improving its error by modifying its decision surface, it ends up creating very flat regions around the training points, which means that the gradients are very small. However, this allows the adversary to use an undefended substitute model, which still has gradients because no defense was applied to it, to find the adversarial examples and transfer them back to the defended model, which will still be making a mistake because it did not improve sufficiently its decision surface. So I'm not going to go into more details, but if you're interested in reading more about this topic, I recommend that you check out cleverhans.io, which has more in-depth blog posts on this topic. So if you're interested in experimenting in this area of research, I recommend that you check out the cleverhans library, which I created jointly with Ian Goodfellow, which allows you to benchmark models against adversarial example attacks, as well as to increase the model's robustness through defenses such as adversarial training. And as always with open source projects, your contributions are very welcomed. If you're also interested in security and privacy in machine learning, you can also read more about these topics on the cleverhans.io blog that I just mentioned. So to conclude this talk, I'd like to stress two things. First, adversarial examples are an instance of worst-case domain shifts. So in machine learning, a domain shift occurs when the training and test distribution are different. Adversarial examples are an instance where the adversary is manipulating the test distribution, which ends up being completely different from the training distribution. So the machine learning model is not able to generalize well to these new inputs. For instance, if you trained a machine learning model to recognize coffee mugs by showing it pictures of coffee mugs from the side, you will not expect it will recognize coffee mugs when shown a coffee mug from the top. Finally, adversarial examples are very useful when considering a wide range of AI problems, for instance, AI safety. So there is a lot of hypothetical discussions about what would happen, for instance, as we deploy driverless cars. And what's nice about adversarial examples is they're a tangible way to approach these problems because they allow you to test the performance of the machine learning model in worst-case scenarios that you can generate. So as long as we're not able to be robust against adversarial examples, we cannot completely trust the predictions of a machine learning model. So with this, I'd like to thank you for your attention, and I'll be going over the chat to take any questions you may have. All right, so I see one of the first questions is what would happen if the remote system, if we don't know the architecture. So I guess this is what I wanted to show with the transferability matrix, is that it does not really matter what model the attacker is using because there is strong transferability across many pairs. And actually what we found is that as an adversary, if we use a logistic regression or a deep neural network, we're very often successful against many models, including neural networks, logistic regressions, support vector machines, and decision trees. So it's not an issue if the adversary doesn't know what machine learning technique is being used, because again, we have very strong transferability. Another question is some other examples of applications of adversarial examples, like the stop sign example that we give. So another example would be malware. So what we found is that using the same attack heuristic, we can basically use adversarial examples to get a roadmap for modifying an Android application which has malicious behavior in order to evade the detection by a machine learning model. So let's say you're using a machine learning model to detect Android applications that contain malicious code. So if you use adversarial examples, you're going to compute a saliency map, which will tell you what features in the Android application you need to modify in order to change the model's prediction from being malicious to benign, so you can evade the machine learning model's prediction. So the only constraint...
Oh, I'm sorry. I didn't mean to cut you off there, Nicholas. I was just going to jump in here. Let me just add a little bit more onto what Nicholas was saying. So any domain in which the output is something that the adversary wants to manipulate, if you look at things like high-speed training algorithms, if you look at I think we were talking about in the security domain, things like network-based attacks, which are using machine learning to identify an incoming attack. Often the adversary will want to know something about the system that's detecting the incoming attack in order to evade detection. And so these techniques we're beginning to show, certainly in the malware case, but also in the network attack space, are extremely effective. Sorry about that, Nicholas.
Yeah, so I was just explaining how we can basically use adversarial examples to target Android applications detectors, so detectors that are trying to detect malware contained in Android applications. And so the only constraint that the adversary needs to add to the saliency map process is that the saliency map should only consider features that are modifiable by the adversary. So for instance, in an Android application, usually the detector will consider both features from the manifest, which are metadata, and features from the code. And as long as you're only modifying features from the manifest by adding new lines, new XML lines to the manifest, you can, we found that you can evade detection by a machine learning model without changing the code, so you still have the malicious behavior in your applications. If you're interested in this, I recommend you can send me an email and I can send you a pointer to the paper. So there's another question which basically asks what happens when you train the machine learning model on adversarial examples. And so this is basically the idea behind adversarial training. So what happens is the defender generates adversarial examples during the training process proactively, and then teaches the machine learning model how to correctly label them. So what we found is that this process is effective to defend against known attacks. So as long as you're aware of the attack that the adversary is going to use, you can defend against it. However, if the adversary changes its attack strategy, then you cannot defend against it because adversarial training will suffer from gradient masking. So again, if you're interested in reading more about this, I recommend you check out cleverhans.io. So that's cleverhans.io. So there's another question about how we can compare the robustness of different machine learning models or deep learning models. So actually evaluating the robustness of machine learning models against adversarial examples is kind of a difficult question because what we're doing is mostly testing the response of machine learning models to adversarial examples. So we craft a set of adversarial examples and we check how accurate the machine learning model predictions are. And what we'd like to do instead is to verify that the machine learning model will give the correct prediction in a certain neighborhood of the test data. And so at the moment, besides doing testing, so generating adversarial examples and comparing how accurate different models are, we don't really have a better way to verify the robustness of machine learning models. But this is a very active area of research, and in the last couple of months, several groups have published a few first attempts at verifying the robustness of machine learning models. And one of the most successful approaches use SMT solvers to verify that ReLU networks were robust in a certain norm ball around the test inputs. So someone is asking for the name of the verification paper. Just give me a second. I just pasted the link to the paper in the chat. Thank you for your attention, everyone, and feel free to reach out by email if you have any other questions. Thank you for listening.